Hi everyone, I am Ranjita HV. I am currently pursuing my degree in Sri Venkateshwara College of Engineering. Today we are going to discuss about the control system. The subject code is BEC 403. In this, the electrical analogy of a mechanical and the thermal system. The two systems are said to be analogous to each other if the following two conditions are satisfied. The two systems are physically different. Differential equation modeling of these two systems are same. Electrical system and the mechanical system are the two physical different system. There are two types of electrical analogy of the translational mechanical system. The force voltage analogy and current voltage analogy. In this, the mechanical translational system. In mechanical translational system, there is a three basic elements that are mass, spring, and the dashboard. In this, the analogous electrical element in a force voltage analogous for the elements of mechanical translational system. In force voltage analogy, the mathematical equation of translational mechanical system are compared with mesh equations of electrical systems. The force F is equal to the voltage E and the velocity V is equal to current I and displacement X is equal to charge Q and the frictional coefficient B is equal to a resistance R and mass M is equal to a inductance L, and also the stiffness K is equal to inverse of capacitance 1 by C and the Newton's second law of Kirchhoff voltage law. For the force balanced equation for the mass dashpot and the spring elements, let a force F be applied to an ideal mass M. The mass will offer an opposing force Fm which is proportional to acceleration. The F is equal to Fm is equal to M d square x by dt square. And let a force F be applied on the ideal dashpot with various frictional coefficient B. The dashpot will offer an opposing force Fb which is proportional to velocity. That is F is equal to Fb is equal to B into dx by dt. Next, let a force F be applied to an ideal spring with a spring constant K. The spring will offer an opposing force Fk which is proportional to the displacement, that is F is equal to Fk is equal to K into Kx. Let us see some examples. The force balanced equation of the idealized elements. Let us consider an ideal mass element as shown in the figure, which has the negligible friction and elasticity. Let force be applied on it. The mass will offer an opposing force which is proportional to acceleration of the body. Here the F is the F is the applied force and Fm is opposing the force due to mass. The Fm is inversely proportional to the d square x by dt square, or the Fm is equal to m into d square x by dt square. By the Newton's second law, we can write this formula as F is equal to Fm is equal to m into d square x by dt square. Next, consider an ideal frictional element dashpot as shown in the figure, which has a negligible mass and elasticity. Let a force be applied on it. The dashpot will offer an opposing force which is proportional to the velocity of the body. Here the F is the applied force and Fb is the opposing force due to the friction. Here the Fb is inversely proportional to dx by dt and Fb is equal to B into dx by dt. And by the using a Newton's second law, we get F is equal to Fb is equal to B into dx by dt. For next, when the dashpot has the displacement, both the opposing force is proportional to the differential velocity. That is, the Fb is inversely proportional to d by dt into x1 minus x2, or Fb is equal to b into d by dt into x1 minus x2. Here, by the ideal dashpot with a displacement at the both the ends, we will get the Fb is equal to B into d by dt into x1 minus x2. Let us consider an ideal elastic element springboard as shown in the figure. when the spring will offer an opposing force which is proportional to the displacement of the body. That F is equal to the applied force and Fk is equal to the opposing force due to elasticity. Here the Fk is proportional to the x, or the Fk is equal to k into x. By using a Newton's second law, we will get the Fk is equal to k into x. When the spring has a displacement at both the end as shown in the opposing force is proportional to the differential displacement, that is Fk is inversely directly proportional to the k1 minus k2. Here the Fk is equal to k into x1 minus x2. Here we are going to use the Laplace transform. Here are the sum of the formulas for the Laplace transform. That's x of t. When we're going to apply the Laplace transform, we will get the x of s. Same thing, we are going to apply the dx of t divided by dt. When we're going to apply the Laplace, we will get the s into x of s. Next, for the d square x of t divided by dt square, when we're going to apply for the Laplace for this equation, we will get the s square into x of t, x of s. Then next we are going to discuss about some of the example problems for this. Write the differential equation for the mechanical system and determine the transfer function. Here we can see this picture. The K1 is acting on the M1, the B1, the B3 and the K are applied on to the M2 and also and M1. These two B and the K are acting on both the M1 and M2. Here we are going to first take the equations, the free body diagram of mass as shown in the figure and opposing the force acting on the mass one. Here the Fm1 is equal to m1 into d square x1 by dt square, and Fb1 is equal to b1 into dx1 by dt. And also we have the B1 is acting on both the M1 and M2. So we are going to take as B into d by dt into x1 minus x2. Then Fk is equal to k into x1 minus x2. By the Newton's second law, we're going to write the M1 plus Fb1 plus B plus Fk1 plus k is equal to 0. We are going to add all the M1 and B1 and Fb1 and Fk. And next, on taking the Laplace transform of above equations with the 0 initial, we will get, we are going to apply the Laplace for this equation. For d square x1 by dt square, we will get the s square into x1 of s, plus for b1 into dx1 by dt, we will get b1 into s of x1 s. Again, we are going to apply for all the equations for the Laplace transform. And here we will get, by taking the common of x1 of s, we will get the x1 is equal to x of s into ds plus k divided by m1 s square plus b1 plus b2 into s plus k1 plus k. The free body diagram of the mass M2. First, we have written the x1 at the node x1. Now we are going to write the equation at node x2. Then the f of m2 is equal to m2 into d square x by dt square, and fb2 is equal to b2 into dx by dt, and fb is equal to b into d by dt into x2 minus x1, and fk is equal to k into x2 minus x1. By Newton's second law, the fm2 plus fb2 plus fb plus fk is equal to f of t. Here the m2 into d square x by dt square plus b2 into dx by dt plus b1 into d by dt of x minus x1 plus k into x minus x1 is equal to f of t. On taking the Laplace transform of above equation with a zero initial conditions, we will get, then for this equation, we are going to apply the Laplace and we will get, and here we are going to take the common of the x2 of s. Already we have gotten the x1 of s and we are going to substitute the x1 of s here. And by substituting the x1 of s from the one in equation 2, we will get this. Here we are going to prove that the x of s divided by f of s. Then we are going to take the f of s outside and we will get the equation like m1 of s square plus b1 plus b of s plus k1 plus k2 of s divided by m1 of s square plus b1 plus b2 of s plus k1 of k2 and the m2 of s square plus b2 plus b1 of s plus k minus bs of ks square. These are the condition we need to prove for this question. Next, for the result, the differential equation growing the system or m1 of s and the transfer function of the system is x of 4. This is the equation we need to get. Thank you, everyone.